Okay, so you guys have learned arithmetic sequences and geometric sequences before, but I just feel like last year when you learned it, it was just sort of overrated. It's like sort of overemphasized. And then you guys are at the age where you're taking the SAT also, and it is way overemphasized on the SAT. It's like the only kind of sequence pretty much they ever put on there, except sometimes they put in the Fibonacci to kind of sneak that in. Okay, but an arithmetic sequence is really just a linear sequence. We've been talking about growth rates of sequences the last couple days, right? So remember one of the sentences we wrote, it was actually the last sentence we wrote yesterday, period 4. The last sentence you wrote was, if the first difference is common, or if the first difference is constant, the pattern is linear. Maybe you remember us writing that yesterday. This is the last sentence you wrote yesterday. We had 3 sentences, remember? Okay? So what we were talking about was something that looks like this. Let's just call it C sub n. That way you don't think it's always A sub n. 7, 12, 17, 22, 27, etc. Okay? So why are we calling it a linearly growing pattern? It's because if you look at the difference, the rise you could say, the first difference is a constant. It's plus 5 on every iteration. So this must be a linear growth. Okay? All right, so let's see if we can figure out the formula for the linear growth. So we know that 12 is really just 7 plus 5, right? And 17 is 7 plus 5 plus 5. And 22 is 7 plus 5 plus 5 plus 5. So let's analyze that real quick. There's a pattern here, obviously. You'll notice that every term after the first is 7, of course, plus a certain number of 5s. So right now I'm on the second term. The second term. How many 5s do you see? 1. Now I'm on the third. Let's put the phones away. Okay. Now we're on the third term. How many 5s do you see? 2. Now we're on the fourth term. How many 5s do you see? 3. If we go on to the fifth term, how many 5s will we have? 4. That's right. So the fifth term has 4 5s. Right. If you went all the way out to the, let's say, the 100th term, so if you wanted to find C sub 100, there would be a 7. And can you guess how many 5s there would be? 99. There'd be a total of 99 5s. It's just a pattern, right? There would be 99 5s. Now this is, of course, a conjecture, but it seems reasonable enough, right? Every time you're at the nth term, you have a 7, of course, and you have a certain number of 5s. It always seems like you've got one less 5 than you're on, than the space you're on, right? And actually, that's the basic rule here. It's first term plus a certain number of 5s, right? So nobody would want to write 5 99 times. We would just write what? 99. Obviously, 99 times 5, right? Repetitive addition is the same thing as multiplication. So this is 7 plus 99 5s. So what exactly was the 7 again? What was that 7? What does that mean? The first term. And what does the 5 mean? That's our growth constant, right? So basically what we're saying is if you wanted to find any term, C sub n, you would start with what? 7, right? In other words, the first term, right? And then you would add on n minus 1 5s, or if it's not a 5, it could be some other difference. It could be any difference. So this, I'll use A here because the book does. This is the formula for finding the nth term of an arithmetic sequence. It's actually not very hard to figure that out if you forget this formula. You can kind of recalculate it. It's a very simple idea, too. If I wanted to have Jace move to the fourth seat in this row, let's say I want Jace to move to the fourth seat in this row. You don't have to. I was being hypothetical. Basically, he would have to only move 3 seats, right? Obviously, he's going to move backwards 3 spaces because his first seat doesn't involve a move, right? The same thing is true here. If you want to find the 100th term, you only have to add the 5 99 times because the first term doesn't include an addition of 5. It was just sort of there, right? Okay, so this formula, maybe you've seen this before. I know you have in Algebra 2, except instead of using a, they use lowercase t. And I know if you've done the SAT anytime recently, you've done this formula, okay? If you've been studying for the SAT. How many of you have seen this formula since last year? Like, the last time you saw it was not a year ago. It was actually more recent. Anyone in that category? Interesting. You take the SAT, yeah. So anyone who studied for the SAT has used this formula. Yeah. So this is cool because now I can give you a first term, first couple terms of a series or sequence, and you can find like the 999th term. Okay? So let's do that real quick. That's a really straightforward problem. Probably not how I test you, right? Let me show you just some sample problems. So let's say I say find the 25th term of the arithmetic sequence. Okay, so I'll give you the first couple. Oh, by the way, I have to kind of tell you it's arithmetic. If I don't tell you it's arithmetic, then you won't really know the pattern, unless I give you a ton of terms and it's obvious. So I'll just tell you, usually it's arithmetic. Okay, so let's give you, I'll give you 3 terms, okay? -5, 3, 11. But you need the 25th one, right? So it would be kind of childish to add 20, to go ahead and get out a calculator, you know, and keep adding. That's not really our objective here. Try to use the formula we derived a minute ago, right? 25th term, you would be taking your -5, and you'd be adding 24 of something, right? So go ahead and write the left side too. If you didn't write a sub 25, do that because that's what it means, 25th term, right? It's good to write the notation. And what is it? What is my first difference on this particular sequence? 8, right? Okay, so that's my first difference, and so this comes out to 192 minus 5. 187, I think. Does that sound right? Yeah. Okay. So do you think I'll give you a test problem like that? No. Probably a little too easy, right? How about this one? The last 2 terms of an arithmetic sequence are a sub 19 equals 101 and a sub 20 equals 107. Find the first term. Okay? So see what you can do with that. You can use the formula as much as you want, but it sets up a little differently. You're actually not looking for the last term anymore. See? You're looking for the first term, so you're going to have to use a little bit of application there. If you're stuck, I would suggest you just make some assumptions, right? The fact that I said that these are the last 2 terms, A19 and A20, tells you that there's how many terms? It's not stated, but it's implied that there are 20 terms, right? So if there are 20 terms, then you can just use n equals 20 as your n value. So, for example, when you write the formula, you might as well just write this at the beginning of every problem, right? You know that n is 20, so you can actually plug that in right here and here, both. Always treat your formulas as 2-sided. You don't want to just plug in on the right, you know? A lot of people think, oh, I'll just figure out the right side. That's not good enough. Actually, your unknown is right here, right? So you're going to need to flush out both sides of this equation, okay? All right, so left side is a sub 20. see? And this is your a sub 1, and this is 20 minus 1 times d. So this time I actually gave you a sub 20, that's your 107. How many of you have 107 equals for this problem? You have a 107 equals? Good. And then there's a 19d. Now what is d? It's not stated, but it's implied. What is d? It's 6, right? It's the difference between any two terms, and here we're given the 19th and 20th term. So you should be able to tell that d is 6 from this, and you should be off and running now. Probably don't need to finish this problem. What did you guys end up with, though? Are you surprised to have a negative answer here? I thought we said we were going to have counting numbers only. 1, 2, 3, 4, 5. That's for n, right. So our input, our domain is positive integers. The output can be anything. I never said anything about output. Right? Sometimes we even get fractions or irrationals or whatever. Okay, so that's the answer. What happens if we plot this sequence? So we now know that the first term is -7. That gives you a dot here. But I'm not talking about just plotting it out. I'm asking what shape it should take on. There should be a line because it rises by 7 every time we run one, right? So it's going to go up 1 every single time. I mean, up 7 every single time. You see the linear pattern there? Okay. Quick reminder, how did we know that the pattern was linear? It's given, right? It says it's arithmetic sequence, which means first common difference is a constant, which means it's linear growth. Okay, let's try this one. This is a really hard one. Okay, harder one. The arithmetic sequence b sub n has b sub 10 being 12 and b sub 9 is 50 more than b sub 20. Find b1. Don't expect a nice answer, but use your critical thinking skills to see what you can set up and solve. Okay, so now let's finish this problem. So B10 is 12, B9 is 50 more than B20. So you can kind of start writing down truth statements. Okay, so one truth statement, one thing you can always do is turn an English sentence into an equation. A statement like B9 is 50 more than B20 can be written mathematically simply as B9 is 50 more than B20, right? So that's one little clue. There's another relationship between B9 and B20, right? B20 would be B9 plus a certain number of D's, right? How many times would you have to add a common difference to the 9th term to reach the 11th term? That's right, 11 times. Okay, so you really have two equations here, right, that relate B9 to B20. Unfortunately, D just popped up its ugly head. Okay, but there's another statement we can write down. Isn't it true that B9 is related to B10, right? B9 is related to B10 in that they're neighbors, right? So I just drew 20 blanks. I've shown you B9 and how it's sitting right next to 12. That's B10 as given, right? So it was green originally. Highlight that green. Okay, so one more relationship. B9 is simply 12 minus the common difference. B9 is simply 12 minus the common difference. All right. So with a little substituting and a little hard work, we can probably figure this problem out. Ultimately, we seek D, which means we'll finally want, or actually ultimately we seek B1, but we'll have to get D in the process, okay? Most likely. So let's go ahead and make some substitutions. All right? So let's look back at our first equation. B9 is 50 plus B20. Why not change that to B9 is 50 plus, and we just found a suitable expression to replace B20. It's right here. So instead of B20, we will write B9 plus 11D. You'll notice that the B9's cancel from the problem, and we end up with D is negative 50 over 11. So D was almost negative 5. It was almost a negative 5 common difference, but not quite. Okay, now that we have D, that's a huge boost. We can go ahead and find B9. So B9, we said, was basically 12 minus D. That's from this equation up here in pink. Right? B9 is 12 minus D. We just found D. So D is, remember, negative 50 elevenths. So this comes out to be 12 plus 50 elevenths. Or you could say 132 plus 50, so 182 over 11. Not a very friendly B9. Now we seek B1. So here's the final clincher. We never wrote down the formula that we learned in the first place. AN equals A1 plus N minus 1D. We never actually wrote that. Of course, the name of this particular sequence is B, so we'll write in a B here. B sub n is B1 plus n minus 1 times D. And now that we seek the first term, we can use some of these things we know. For example, we know B9 is 182 over 11. This is B9. And the ninth term is B1 plus 9 minus 1 common differences. So since this is B9, I have a 9 right here. B9, so we have a 9 minus 1. Now we just need to solve for B1, and then we'll be done. I realize now I didn't even have to find B9. I could use B10 to solve this part, but that's okay. I don't always have to do it the fastest way, as long as we get through it, right? So we have 182 over 11 equals my mystery B1 plus, and then it's 8 times negative 50 over 11. So it's basically negative 400 over 11. And if you add that to the other side, you get 582 over 11. So this is just a cut above others, right? For one thing, it would have been nice if I'd given you the difference between the 10th and the 20th term, so the 9th and the 20th term. Then your B would have actually been, your D, your common difference, would have been exactly 5, not 50 elevenths, and it would have made this problem quite a bit easier. But our goal isn't always easier, just understanding, right? So maybe you could try this problem again, just take a totally different approach, try it on your own.